In this episode, we focus on data quality as a practical safety tool, not as a perfection hobby. Beginners sometimes hear data quality and assume it means making the data look neat, like cleaning up a messy room so it feels organized. For AI, data quality is more like checking whether the ingredients going into a recipe are fresh, accurate, and suitable for the meal you are trying to cook. If the ingredients are wrong, the final dish will be wrong. And with AI, the wrongness can scale quickly and affect many people. Data quality rules are the expectations you set for what data must look like to be safe and useful, and validation is the act of checking that those expectations are actually met. The reason this matters so much for AI governance is that errors and bias often have a shared root, which is that the data is incomplete, inconsistent, or unrepresentative in ways that create predictable harm pathways. If you can validate data quality rules consistently, you reduce the likelihood of incorrect outputs and you reduce the risk of unfair outcomes that disadvantage certain groups. The goal today is to learn how data quality rules connect directly to errors and bias, and how to validate those rules in a way that supports measurable risk reduction. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. To build a beginner-friendly foundation, it helps to define what we mean by data quality in a way that goes beyond vague words like good data. Data quality includes accuracy, meaning the data reflects reality as intended. It includes completeness, meaning necessary fields are present and not missing in systematic ways. It includes consistency, meaning the same kind of value is represented the same way across records and sources. It includes timeliness, meaning the data is current enough for the purpose and not stale in ways that distort patterns. It includes validity, meaning values fall within allowed ranges and formats. It also includes representativeness, meaning the dataset covers the kinds of cases and populations the AI system will encounter, rather than overrepresenting some and underrepresenting others. Beginners should notice that these dimensions are not just technical, they connect to real harms. Missing data can cause errors that cluster around certain groups. Inconsistent labeling can create unpredictable outputs, and unrepresentative data can produce biased behavior even if the model is built correctly. Data quality rules are how an organization sets expectations for these dimensions, and validation is how you prove those expectations are being met rather than assumed. The next step is understanding why data quality is a major driver of AI errors, because AI systems learn patterns from data and then apply those patterns in new situations. If the data includes incorrect values, the model can learn incorrect relationships, which can produce outputs that are confidently wrong. If the data includes duplicate records or inconsistent representations, the model can overweight some patterns and underweight others, which distorts outputs. If the data is missing key context fields, the model may rely on weaker signals, producing errors that look mysterious but are predictable from the missing information. Beginners should also recognize that errors are not always random. If data quality problems are systematic, the AI errors will also be systematic, meaning certain types of cases will fail more often. Systematic errors are dangerous because they can repeatedly harm the same users or situations. Data quality validation is therefore a form of prevention because it reduces the chance that the model learns flawed patterns in the first place. It also improves reliability because it makes model behavior more predictable across contexts. Bias is often discussed as if it is a purely moral issue, but it is also a data issue in many practical situations. Bias in AI outputs can arise when the data reflects historical unfairness, when certain groups are underrepresented, or when labels and outcomes encode past decisions that were not fair. Beginners should notice that bias is not always obvious in the dataset, because it can be hidden in proxies, like zip code patterns that correlate with socioeconomic status, or in performance differences across groups that appear only when you measure outcomes. Data quality rules help reduce bias by enforcing representativeness checks, consistent labeling, and careful handling of sensitive and proxy features. Validation is what reveals whether these rules are actually working. If a dataset is missing coverage for certain groups, the model may perform worse for those groups, which can create unfair outcomes even when overall accuracy looks fine. If labels are inconsistent across different subpopulations, the model may learn different rules for different people, producing unequal treatment. Beginners should see that validating data quality is one of the most direct ways to reduce bias risk before a model ever reaches production. A useful way to connect quality rules to risk reduction is to think in terms of specific quality failures and the harms they create. When completeness fails, the harm can be that the model lacks information and substitutes unreliable cues, increasing error likelihood. When consistency fails, the harm can be that the model treats the same situation differently depending on how it is recorded, producing unpredictable outputs. When validity fails, the harm can be that the model learns from impossible values and produces outputs that reflect noise rather than reality. When representativeness fails, the harm can be that the model performs well for common cases and poorly for less represented cases, which can create unequal outcomes. When timeliness fails, the harm can be that the model learns outdated patterns and makes decisions that do not match current conditions. Beginners should notice that each failure suggests a control, which is a data quality rule, and each rule suggests a validation approach, which is how you check whether the control is operating. This is what makes data governance measurable. The rule is the expectation, and the validation provides evidence. When you can show validation results and how they influence decisions, you can defend claims about risk reduction. Validating data quality rules begins with choosing rules that are tied to the intended use of the AI system, because quality is not one universal standard. A dataset might be perfectly adequate for one purpose and inadequate for another. Beginners should think of this like a map, where a city map might be great for driving but not detailed enough for hiking trails. For AI training, quality rules should reflect the decisions the model will support and the populations it will affect. If the model will be used in a high-impact context, quality rules should be stricter and validation should be more thorough. If the model will be used in a lower-impact context, rules can be lighter, but still need to address basic risk factors like missing values and inconsistent labeling. The key is that the rules are explicit and the validation is repeatable. When rules are implicit, teams may assume the data is fine because it looks familiar. When rules are explicit, teams can prove the data meets minimum standards or can identify where it does not. One important validation principle is to check for distribution and coverage, because representativeness is a major driver of bias and error. Coverage validation asks whether the dataset includes sufficient examples across the situations the model will face, including less common but important cases. Beginners should notice that rare cases can be high impact, like unusual but serious conditions in a medical context or uncommon fraud patterns in a financial context. If the dataset lacks these cases, the model may fail when it matters most. Coverage also applies to groups of people when the system affects individuals, because underrepresentation can lead to performance differences that become unfair outcomes. Validation here might include checking whether the dataset includes a meaningful spread across relevant categories, and whether any category is missing or extremely sparse. The goal is not to force perfect balance, which may be unrealistic, but to make gaps visible and to decide how to handle them. A visible gap can be mitigated through additional data collection, adjusted scope, or stronger human review. An invisible gap becomes a hidden risk that is difficult to manage. Another key validation area is label and outcome consistency, because many AI systems rely on labeled examples or structured outcomes. If labels are inconsistent, the model learns inconsistent rules, which increases errors and can create unfairness when inconsistency correlates with certain groups or contexts. Beginners should understand that inconsistency can come from multiple labelers, changing definitions over time, or differing standards across teams. Validation should therefore include checking whether labeling guidelines exist, whether they were applied consistently, and whether certain categories show unusual disagreement or variability. If disagreement is high, the data may not be reliable enough for the model to learn stable patterns. It also helps to check whether outcomes reflect what the organization intends to optimize, because historical outcomes may encode past decisions that were influenced by bias or constraints. If the model is trained to reproduce those outcomes, it may reproduce those patterns as well. Validating labeling and outcomes is therefore both a quality control and a fairness control. When labeling is stable and aligned with intended goals, the model is less likely to learn harmful shortcuts. Missing data is another area where validation can directly reduce errors and bias, because missingness is often not random. Beginners might assume missing values are just minor imperfections, but missingness can cluster, such as missing fields being more common for certain users, certain regions, or certain channels. When missingness clusters, the model learns a skewed view of reality and may treat similar cases differently depending on which fields are missing. Validation should therefore examine not only how much data is missing, but also where and for whom it is missing. If certain groups have more missing data, the model may have less information to make accurate predictions for those groups, increasing error rates and unfair outcomes. Data quality rules can require minimum completeness thresholds for key fields and can require investigation when missingness patterns are uneven. When missingness cannot be fixed, mitigation might involve limiting scope or requiring human review for cases with low data quality. The point is to make missingness visible and managed rather than allowing it to silently degrade performance for certain people. Outlier and anomaly validation also matters, because extreme values and unusual patterns can distort learning. Some outliers are real and important, while others are data entry errors or measurement glitches. Beginners should notice that AI models can sometimes latch onto outliers as strong signals, which can produce strange behavior in production. Validation should therefore include checking whether outliers are plausible and whether they reflect the intended measurement. It should also include checking for impossible values, like negative ages or dates in the future where they should not exist, because those values indicate data quality failures. Rules can define allowable ranges and formats, and validation can test whether the dataset respects them. This kind of validation reduces errors by removing noise and reduces bias by ensuring that some groups are not disproportionately affected by measurement errors. For example, if certain systems produce more errors for certain populations, the data may include more anomalies for those populations, leading to model performance differences. Validating anomalies is therefore not just cleaning for neatness. It is controlling a risk factor that can create uneven outcomes. Data leakage is another critical quality and governance issue, and beginners should treat it as both an error risk and a fairness risk. Leakage means information that should not be available to the model at training time is included, making the model appear to perform well while actually learning shortcuts. For example, a field that directly encodes the answer or a post-decision outcome that would not exist at prediction time can leak. Leakage creates a dangerous illusion because the model looks accurate in testing but fails in real use. It can also create unfairness if the leaked signals correlate with certain groups in ways that distort behavior. Validation should therefore include checks for features that are too predictive, checks for timing consistency, and checks for fields that should not be used. Beginners should notice that leakage is often accidental and can happen when datasets are assembled quickly or when teams reuse existing data without rethinking what is appropriate. Quality rules should define which fields are allowed and which are prohibited, and validation should confirm compliance. Preventing leakage protects reliability because it ensures performance estimates are honest, and honest estimates are necessary for responsible deployment decisions. Bias reduction through data quality also depends on recognizing proxy features and contextual gaps. Proxy features are variables that can stand in for sensitive traits, and contextual gaps are missing context that causes the model to rely on proxies. Beginners should understand that a model does not need explicit sensitive data to produce unfair outcomes. It can infer patterns indirectly. Data quality validation can help by examining whether certain features are acting as proxies and whether removing or controlling those features changes outcomes. It can also help by improving the completeness of context features so the model does not rely on weaker signals. Another part of bias-related quality validation is checking whether the dataset reflects the real operational environment, because mismatched environments can produce uneven errors. If a dataset is drawn from one region or one channel, the model may perform worse in other regions or channels, which can correlate with demographic differences. Validation should therefore examine whether the dataset covers the environments where the model will be used. When environment coverage is poor, mitigation might involve limiting deployment scope or collecting additional data. The point is to treat representativeness as a quality requirement tied to fairness outcomes, not as an optional ethical add-on. To make these quality rules auditable and operational, validation must produce evidence that is consistent, repeatable, and linked to decisions. Evidence includes documented rules, documented validation results, and documented actions taken when validation fails. Beginners should notice that validation is not complete if it merely discovers problems. Validation is complete when it drives a decision, such as fixing data, adjusting scope, increasing oversight, or delaying deployment. Auditors will look for that connection because it demonstrates governance is effective. They will also look for whether validation is performed regularly, especially when data sources change, because quality can drift. A dataset that was high quality last month may be lower quality today if upstream systems changed. Repeatable validation routines are therefore part of ongoing risk management, not just a pre-training checklist. When validation is built into the lifecycle, it helps detect drift early, reducing both likelihood and impact of harm. This is how quality rules become real controls. The central takeaway is that validating data quality rules is one of the most direct ways to reduce AI errors and bias because it addresses root causes before they become scaled outputs. Data quality is multidimensional, including accuracy, completeness, consistency, validity, timeliness, and representativeness, and each dimension connects to specific harm pathways. Poor completeness, inconsistent labeling, unrepresentative coverage, anomalies, leakage, and proxy reliance can all drive systematic errors and unequal outcomes. Quality rules define what acceptable data looks like for a specific intended use, and validation provides evidence that those rules are being met or reveals where they are not. When validation results are linked to decisions and repeated over time, mitigation becomes measurable because you can show how controls reduced risk indicators and improved reliability. For beginners, the most important mindset is to treat data quality as a governance control that protects people and trust, not as a cosmetic cleanup task. When you do that, you build AI systems on foundations that are not only technically stronger, but also more defensible and fairer in real-world operation.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit BareMetalCyber.com.